So thank you, Theo, for the introduction. So Silvio and me, we would like to present one topic which comes out of an ongoing research project. And in this research project, we are using a technology which is provided by the company Crelos, and Silvio represents this company. So it's a small company which he will introduce in the next slides. And we are using some infrared heaters here, which are commonly used to heat up thermoplastic materials to cure thermoset-based composites. And today we want to give you an overview of what we have done in the project. And we would like to show you a little bit that this technology has a high potential and is able to perform very well and to reduce process cycle time, and beside also could decrease the cost itself. So therefore, we have a small agenda. So first of all, we do a short introduction, and then we will present you the concept and approach. Then we have some benchmark examples which are related to experimental trials, and also our approach where we use simulation to modify the process, and then in the end the summary. So first of all, we would like to introduce ourselves. So my name is Christian Brauner. I'm working at the University of Applied Science in Northwestern Switzerland. So you can see here a nice image. We are not located in the region where the highest mountains are, so it's close to the German border. And we are a kind of research institute with around 40 people, which are doing applied research all around polymer materials. So starting from formulation side, polymer processing, and also design. And maybe if you come from the German side, Fachhochschule, University of Applied Science is something which is not so commonly in research, but in Switzerland this is a little bit different because these institutes have a strong focus on applied research. So this is all which I would like to say to my institute. And so I would like to hand over to Silvio now, and he will introduce Crelos and also their specialty by their products for infrared heaters.
Yes, thank you very much, Christian. Dear webinar listeners and viewers, a warm welcome also from my side. My name is Silvio Conti, and I've been working for Crelos for 15 years now. Currently, I'm working as a sales manager. What is Crelos AG? Crelos AG is a manufacturer of high quality infrared heaters. These infrared heaters are the heat source of the project presented here and the decisive factor which made the project successful. For a better understanding of the process, which Mr. Brauner will explain you later, it is therefore important to learn a bit and a little more about these heaters. So my introduction would be maybe a bit longer than just a few words. And I will start with a company overview, some company figures. It was founded in 1975. All started with a newspaper advertisement from a printing company from overseas. And this company was looking for someone who manufactured infrared heaters for printing presses. They didn't want to build the heaters themselves anymore. And the young engineer, Mr. Bernhard Lüscher, took the chance and established the company Krelus and starts building infrared heaters. Mr. Lüscher and Mr. Krebser founded in 1975. Mr. Krebser was only a few years there, and Mr. Bernhard Lüscher managed the company until 2008. And then the management buyout by the long-time employees, Mr. Hans Jordi, some of you know him maybe, and Mr. Lüscher, together with Mr. Werner Haueri, secured the further existence of this company. 10 years later, in 2018, Leicester was overtook the company Krelus. Leicester is a big company which makes process heat products, hot air hand tools, welding tools, and some specific high precise sensors. And the continued existence of the high quality Krelus products is thus ensured. We have a global presence over 100 countries, deserved by a lot of representatives in these countries. And as you see, our production space is not so big. We only have 26 employees. We are located in the middle of Switzerland in Oberentfelden. Because of the acquisition by Leicester, we are moving in the end of 2018 to their place near Luzern and will be integrated step by step in this company. As you see on the right side, you see one of our heating fields with some modular infrared heaters. I will explain later. All products of Krelus are made, designed, developed, and manufactured in Oberentfelden. So let's talk about some products. What products does Krelus AG manufacture? The core competence and the ambition of our company is to produce the best infrared heaters available on the market. Krelus does not build machines or plants and does not do automation. We concentrate on the heaters. Every infrared heater which we made works according to the same operating principle. It is a medium wave metal foil heater. This metal foil is made to glow by a flowing current and works perfectly in oxygen atmosphere. It is therefore not coated with glass, for example, or ceramic. We make, on one hand, we make profile heaters, custom made. Custom made means different sizes, different lengths. We can make them up to 7 meters in one length. If no zones are required, this is a good product. The heating foil going through the whole length. But for some applications, maybe a machine user treats different sizes of products, maybe 5 meters, 7 meters, 2 meters. Therefore, the profile heater solution is not the best. That's why we invited standardized smaller module IR heaters. You see a picture on the right side. We can build them together to bigger fields, also up to 7 meters or more. But the advantage is that we can switch off several heaters just to treat the material which is running through or which is stationary positioned on the heater. We also make smaller heaters, pin heaters, heat stacking tools for riveting applications, probably for riveting of door panels. And of course, we are making also welding heaters for welding in 2-dimensional or 3-dimensional shape for plastic joining, as I said. 2 parts are being heated up, contour followed, and put together. This technology of welding with contour following metal foil heaters, or in combination with ultrasonic processes welding, this was developed at that time by Krelus and the partner. And nowadays, this is the state of the art. And of course, we are making some special heaters according to the customer needs. Which type of emitter and how they are combined ultimately depends on the process. Applications. The application range of Krillus heaters is enormously diverse. I just written down a few of them. And this has to do with the fact that the emitted radiation is simply optimal for many, many products, almost all plastics, paper, water. And infinitely variable control in real time is possible. The operating principle is heating by means of radiant energy. So where the radiation hits, there it also heating. The use of heaters for the target heating of environments or for heating or as a heating source for an oven is less suitable. There are more efficient solutions for such applications. And the main industries we are in is automotive, of course, aircraft, geotextiles, furniture, materials, not the wood, but the materials which has been used for making the furnitures, food, packaging for food, printing, drying of ink, etc. And typical processes in these industries is coating of different materials. As an example, the deep coating of a glass fiber mesh, curing of Teflon to make, for example, tents that cannot be burned. Of course, there are a lot of embossing applications, as you see on the picture on the right. Laminating of different materials, thermoforming, of course. Thermoforming of carpets, of bins, of bigger parts for trucks, etc. Plastic joining, as said before. For example, rear lights of cars are welded, some with infrared, some by friction welding, or some by laser welding. And of course, we can dry, because the water is also absorbing medium wavelength infrared energy really well. We can dry, or we can pre-dry. Pre-dry normally is a bit more efficient because we can heat up materials, paper with water much more efficiently than with hot air. Hot air is used afterwards to remove the moisture out of the system. Our customers are the plant manufacturers, plant operators who need upgrades, for example, yes, and various institutions such as colleges and universities. And these customers can also be project partners at the same time, like here. And they are supported directly or via Krillus agencies in many countries. I have here a short video that shows just a simple thermoforming application. A sheet is being moved into an upper and a lower heater. If the materials are thin, 1 millimeter or less, an upper heater, one-side heating is sufficient. We heat until we reach the target temperature by measuring the surface of the product. And due to real-time controllability, the heater reacts to keep the temperature. Sometimes dwell time is needed to have a true going temperature. And then it moved to a press. On the upper side, you see this is a hot drape forming application for making bigger parts, flaps. Heating field size is maybe 2 meter by 20 meter. So what are the properties of acrylus heaters? Highest energy efficiency. This means one point is the heater is not covered with glass, simply no covers, just a protection grid to secure the heating foil. Approximately 90% of the radiation comes out. radiates directly to the product. We have a fast response on and off. And the radiated wavelength is medium wave. You see that also on the diagram on the right side. This is the emissivity curve, excuse me, of a Krillus heater. And you see the absorption range in green color of the material in the wavelength spectrum. And you see a lot of them are in between 2.5 up to 4. And in that area, the Krillus heater has the optimum efficiency. We are reaching on our foil 850 degrees. This corresponds to the wavelength of 2.5 micron. We do not emit only one wavelength. Heat sources are always emitting areas. Laser not. Laser will emit just one wavelength, but this is not the topic here. And we can build up a watt density up to 50 kilowatts per square meter. And the temperature of the heat source, no matter if the heater is 7 meters long and has 30 kilowatts, or it is a pin heater where the heating foil, the temperature source is only 2 centimeters, the temperature of the source is always 850 degrees at max temperature. When we have more density, when we have maybe 50 kilowatts per square meter compared to 20 kilowatts, we just make more metal foil material on the same surface. So we are always in the best wavelength. Compared to shortwave heaters, there is no increased starting current by switching on. And they are continuously controllable from ambient to 850 degrees. And this is the best emitted wavelength for most products. I will show you just, I think, 2 important main advantages compared to other heaters, like glass heaters or ceramic heaters. On the one hand, on the left side, you see the emissivity spectra of some infrared radiation sources. These are all lamp heaters, glass heaters, shortwave heater, fast responding medium wave or a carbon heater, and the classical medium wave heater from Krillus. And you see the intensity peaks. So the shortwave heater has a max temperature on the source of 1,800 approximate degrees. But in the necessary absorption area of most products, as we've seen before, and this is between 2.5 and 3.5, the efficiency is quite lower than with a heater that emits the radiation in the right spectrum. As you see, the green color covers almost double as the blue one. So we can install less capacity and have a better effect, a more efficient effect just because of the absorption of the material. On the other hand, on the right side, we compare the reaction time switching on or switching off a heater. Our heater, because of the fast reaction foil, reacts quite fast, the orange curve, compared to a quartz heater or a ceramic heater. So, to conclude this, we emit directly from the radiation source to the product. This makes the heater fast and precisely controllable. The second point is the emitted radiation is in the best absorption range for the most materials. You see that on the left side. And we can combine both advantages together. The quartz heater or the ceramic heater emits energy almost in the same wavelength as the metal foil heater. but they cannot be controlled really fast. The shortwave heaters can be controlled really fast, but have mostly not the right wavelength for plastics, paper, water. So, and neither glass nor ceramic heaters combine these two advantages. I think these are the two most important points of a metal foil heater compared to glass heaters and ceramic heaters. So what is needed for an optimal infrared solution? An infrared product know-how is needed. Infrared heaters should be known, physical properties should be known, the suitability of the heaters to a process, some calculations of a process if possible, and of course a lot of experience to find the right product. Customer and partner know-how is a second point, which is really important. A lot of them have experience with infrared solutions because they are using machines with infrared, so they can give really nice advices of how it should be. This is quite important. Process know-how is needed. This is also mostly in the hands of customers and partners. Some processes we also know because of many years of experience. And to a process know-how, also material tests are belonging to. Then the material should be known, which has to be treated. Mostly also the customer and partners have this knowledge. Also, as for the process know-how, experience and material tests. And then, of course, every heater needs an electrical control. We have some know-how of that. Customers know how they control the heaters. And important are interfaces between heaters, electrical control, and machines. And material tests, last but not least. Some processes are quite difficult or they are new. We have to do first some tests with the materials because calculations only are somehow quite hard. We see it afterwards. Material tests, we can make some material tests in our laboratory, or we use a lot of rental equipment which we give to the customer to make some tests. So all of these points, of these 6 points, are a bit combined together. For some solutions, it maybe only need 1 or 2. For some, needs 4. But this just shows that it's not so easy just to open a catalog, look at the heater and say, oh, I like this one. It's a bit more complicated. So this was my last foil. I think I should give you an overview of this nice product, and we'll pass now to Christian.
Yeah, so thank you, Silvio. So what Silvio has introduced is that we have a heater which has really nice properties, can heat up really fast, and in addition, we are able to customize the heaters and building heat fields with separate elements which we can apply for advanced control. And this was the starting point. So normally, Crelos systems are mostly used in the composite industry by heating up thermoplastic materials or organosheets and so on. And our idea and approach was, what is happening if we apply this technology not to heat up a thermoplastic material? What will happen if we use the technology to control the curing process? And so we were setting us some goals. Can we shorten the curing process? Because if we apply such a system, we are dramatically reducing the thermal mass which we have to heat. So if you think about the huge autoclave, you're heating up tons of materials, the mold, the autoclave itself, the air inside, or the nitrogen gas. And so here we have a system which directly applies the heat into the composite material. And so therefore, can we shorten the curing process itself? Can we reducing the energy? And at the same time, can we reduce costs? So it looks like this. And so our approach was, on one side, to build up an experimental field where we have a kind of heat field with advanced control capabilities. So here you can see our heat field schematic, which consists of 4 multiplied by 7, so in total 28 emitters. Each emitter has around 540 watts with a total power of 15 kilowatt. And as said, we have a PLC-based control to adapt the power of each heater in the heat field. And therefore, we are able to modify this power distribution related to complex geometries with the target that to achieve a homogeneous temperature on the part itself. And in this experimental setup, we are using a lot of sensor systems as well. So in this case, a cure monitoring system from the company Synthesize, which I will show later on. And on the other side, you can see for such a system, you need kind of tool to understand the process, to find a kind of parameter set which you have to apply into this complex heat field, which is dependent on the part geometry. And so therefore we are using a simulation approach, which is modeling the transient radiation. It's including the PLC control from by a simplified PID controller. It consists that we are modeling the thermal conductivity inside the part, and we have also integrated a cure kinetic approach to compute from the temperatures in the part itself the curing reaction and the degree of cure. And so I would like now to present this in details. First, the experimental approach or the experimental work related to the hardware we use, and also on 3 benchmark examples where we want to show you the robustness of the process and the performance. And later on, I will go a little bit in deep into the simulation to show you some animations. So here you can see our setup. So initially, this was a thermoforming machine. And we used the machine different, as I said, for thermoset materials. And here you can see the heat field with some heaters which have different power distribution. So we have a small animation here so that you can see a little bit the process itself. So we have a kind of vacuum setup of this omega-shaped part inside. And we have an open oven, so it's not closed, because we need a certain amount of convection. And the system is controlled, so there's one pyrometer sensor in the heat field which measures the part temperature. And then there's a heat the control system, and here you can see a little bit the properties of the control are not well tuned here, but it's really nice because you can, it was visible that the emitters are flashing a little bit, so you can see this like a small disco. And beside of this, we can measure all parameters, and we can modify, for instance, the control parameters. And this is an example of our cure monitoring. I will go in later on this. And we can also apply an additional cooling here. So you can see there's convection cooling from the top. So some ventilators which can cool the part really fast. So, and now I would like to show you 3 examples. The first one is related to an aerospace application, which was already visible in the video, but I will go in detail a little bit to this. Then we applied one application which is more related to automotive industry. So we applied an infusion process with a really reactive resin system, which is normally used in high pressure RTM, so a system which reacts in 2 minutes. And then I want to show you one additional trial which we have done with the company CMT. So it's a provider for powder-based epoxy prepreg systems, and there we applied an advanced control, a nice demonstration what is possible to follow a complex curing profile. And further possible application, of course, are wind energy or space or sports and so on. So coming to the first example, this you have already seen in the video itself. So there we are curing these omega stiffener, which is somehow related to aerospace application. For instance, if you have the stiffening elements in the A350 Airbus airplane, there you find such omega stiffener which are in the fuselage applied. And the material which we are using here is not a common material. It's not an epoxy-based carbon fiber prepreg. It's a cyanide ester-based prepreg. So it's a high-level thermoset material with a glass transition up to 400 degrees. Normally used up to operation temperatures nearly to 300 degrees. So, for instance, for a turbine or so on. And this material normally has to be cured around 260 degrees. And most of the common manufacturers have the problem that they only have an autoclave which is suitable to go up to 180 degrees. So therefore, the baseline of this process for this material is nearly 16 hours. So you need 8 hours to cure the material at 180 degrees in the autoclave, and then most of the time people apply an additional post-curing in a convection oven at 260 degrees. And so we have taken this example as to show the potential of the technology. So on the left side, the part is demonstrated, and on the right side you can see an upper view, and there you can see the power distribution which we apply in the heat field. And this power distribution was an outcome of our simulation coupled with an optimization approach. And so if we look now to the performance of the system, we can go up really fast to temperature above 240. So here on the right side, we are showing you 3 temperature curves from 3 different trials. So on the left side, you have the temperature, and on the right side, you have the resistance change in the part itself. So this is the system which we use to monitor the curing process. So, and as you can see, we can heat up everything really fast. So in less than 50 minutes, we are reaching a stable temperature above 240 degrees. And the system then reacts really fast. And below you can see the curing process. And the strong advantage is that we can apply heat rates up to nearly 40 degrees per minute. So if you compare this to your autoclave, you're around 1 or 2 degree per minute. So it's accelerating really fast. And so we're able to reduce the process time from 16 hours to nearly 1 hour, or you can see the curing process is nearly over after 30 minutes. So in our newest trials, we applied just 30 minutes. So, and at the same time, we have a total energy consumption of 3.2 kilowatts per hour. So, and if you think now, if you multiply this by the cost of 1 kilowatt hour, which is around 30 cents, you know how much energy you have applied to cure this part. So in comparison to an autoclave, you can imagine, or later I will come back to this issue. So the second trial we performed was with an epoxy system which reacts really fast. And there the approach was that we apply kind of preheating related to for where we have a process window with a stable condition to fill the part. And then we went up to the curing temperature really fast, and this resin system reacts then into, it needs 2 minutes to react. And we applied it to a more complex, or not complex structure, so we are a little bit limited in the size of the heating field. So therefore we scaled a kind of engine hood down to fit into our test case. And you can see again the distribution in the heat field, which was derived by the simulation. And here I am presenting again three different trials. And you can see we varied a little bit with the infusion temperature. And the infusion was really fast and stable, taking around 5 minutes. And then we went up to the curing temperature, and the system reacted really fast. So, and we were again able to heat up above 40 degrees per minute. We performed some measurements to check the degree of cure. And here, because we are not going with the temperature as high, we have a really reduced energy consumption as well. The third test we performed was related to a really special material, which comes from Swiss Composite materials, so from Marcel Schubinger, which is also in the participant list. So it's a really nice material because it's a solid state epoxy-based prepreg. So it's not a liquid prepreg system, which you might know. So the polymer is kind of powder inside of the prepreg, so you can store it infinity long times without any freezing conditions. So it's a nice material, and Marcel is able to answer questions later on, I think, or we can give you the contract direct. And in this case, we used again this geometry, and we followed curing process, which is shown here. So it's also possible to apply a heat rate or this advanced temperature conditions. And so how have we derived which kind of temperature we have to apply? And therefore, we have built up a simulation which is modeling as the radiation, it models as well the control system, because the temperature in the filaments has to be defined by this control system. And we modeled the temperature in the part and the setup itself, also in the vacuum setup. And we added the curing process. So in this animation, you can see the temperature and also the curing of the part itself. And now I want to go a little bit in, or to give you a little bit more inside view. So here we compare the measured temperature of the pyrometer with our simulation, which fits really well. And the blue line, as you can see here, is the PID power output, which we simulated. So in the first part, the system applies 100% power, and then it reduces to nearly 70%, and it's just applying heat when it's necessary. So you have a constant heat flow through the part, through the setup. So on the lower side, a cooling is applied. And so this enables you to react on the process itself. So these resin system which we use in this part is really special and has a huge exothermal energy if you cure this in the autoclave. So this process is not able in a convection oven, because you will create a huge exothermal reaction because you are accelerating the reaction really strong. And then heat is generated, and normally a convection-based system is so slow that you cannot get rid of these heat flow. But our system is capable because it reacts really, really fast. And this is visible also in these curves, which are representing the temperature on different position through the thickness. And there's a kind of trick which we apply. So we have, of course, a vacuum setup, then the composite part, then we have our mold, and then we're applying a kind of isolation system below our mold to avoid huge heat loss through the thickness. So on one hand, we need a small heat flow through the part to being able to avoid exothermal reaction. But at the same time, we can modify this insulation material to decrease the gradient in the part itself. And if you look to the curves, the three upper curves are the gradient in the vacuum setup, because we are applying a two-foil setup to maintain the vacuum, and there's a breather which is blocking a little bit the temperatures. And then we have the gray, black, and blue curve, which are the temperature in the part itself. So the gradient in the part is low, and then the blue curve represents the temperature below the insulation material. So we have a kind of gradient of the temperature through the thickness, and the trick is with the simulation to modify it in that way that in the composite part we have a homogenized temperature without exothermal overshoot in the beginning. So this is again kind of animation, so temperature contours and degree of cure, and you can see that the part cures homogeneous. The upper part is a little bit faster than this region, but related to the different distribution of the heating elements, this is, I think, a good solution. And then, as I said before, we also calculate from the temperature the curing reaction, and we are modeling as well the exothermal heat flow. And because we have used the cure monitoring system in the trials, we can also compare this to our simulation results. So what we are doing here is that we are using a system from the company Synthesize, which is measuring the change of dielectric properties in the thermoset material. So the resin behaves like a dielectric material, a really bad dielectric material, and you can see changes of the resistance during the curing process, because the mobility of dipoles and ions starts to decrease, and therefore the resistance increases. And so the red line represents this change in the resistance, and the green one is the simulated degree of cure. So there's a kind of scattering of the cure monitoring result, because we are using the sensors in a temperature range which is not commonly the range where it's normally used. So normally the system is applied to system around 180 degree. And I think we used it for the first time for this temperatures above 220 degree. So that's why in this region we have a kind of scattering of the measurement signal. Okay. Yeah. Now I would like to go a little bit again into a detail. So as I said, we have this complex setup, and we can play around. And one design factor is the glass fiber isolating material, which is below our mold. And so here you can see the result of a parametric study, which we performed. So we changed a little bit the thermal conductivity, and related to this, we can modify the process. So for instance, the blue curve shows that there's nearly no heat flow through the thickness direction. And then we are getting a huge exothermal reaction, overheating of the part. So the temperature is increasing up to 330 degree. So not a really good process design. But if we tune this a little bit, we can create this heat flow through the thickness, and then together with the applied control of the system, we can reach a nicely smooth heat rate up to this shown 40 degree per minute. So this was my part about the simulation. Now I want to make a short review about cost and energy issues. So if we look to a small size autoclave, and if we apply again the process condition for the cyanide ester based prepack, I know it's a really special material because we have to go to these high temperatures, we can derive some conclusion. So in this case, we have this autoclave, we have the total power of the autoclave. Again, we have to apply curing about 8 hours, and then again do a post-curing in a convection oven. And if we summarize this, we can derive that we need total energy of 145 kilowatt hours. And this means that costs, energy costs are around 36 euros and a process time of 16 hours. And if we compare this now to the infrared controlled curing process, we can reduce the time. The heating is dependent on the part geometry, so we don't have to heat up a large oven. We can tune the heat field, and you can see here there are some heaters which we don't use because our part is not large in this case. And so we can go down with the total energy and the process time. So we reduce the process time because we do not need this post-curing. We can go up to these 270 degrees easily in less than 8 minutes. We can cure the part, we can avoid these exothermal reactions by tuning the setup. And then we end up with a process time less than 1 hour, and we have energy costs less than €1. So which shows the high benefit of the process. So now if I would like to summarize everything, so we have a new process capability, so infrared controlled curing. It's robust and fast, which I have shown with these experimental trials. And we can reduce energy consumption and therefore also costs. But it's always a kind of comparison, so please don't judge on me too hard. So this is an example, and maybe for your case it will be absolutely different. But if you are interested in this, we would like to offer you two things. So on one hand, we are preparing a scientific article which shows a little bit the theory behind, also the material values, and describes the simulation method. And then also we would like to create a kind of guideline how to apply this infrared control curing easily. And if you're interested, we can offer you that we do a kind of experimental or virtual benchmark to you. So my colleague Igor Siliev is also in the participants. He was taking care a lot of the simulation, and due to Corona, we are a little bit limited to access our labs. So what we can do is, if you have interested, or if you were really interested to apply the technology, maybe we can check by a virtual benchmark if this technology fits to your application. So therefore, I'm nearly in time. So I'd like to say thank you. So first to Silvio. So it's a really nice project for us, and we really like to work with you and to interact. Then I would like to thank my colleague Igor. And beside, I would like to thank the InnoSwiss for funding the project, the CATS, the Kunststoffausbildungstechnologiezentrum in Aarau, so there our infrared machine is located, then Swiss Composite Materials and Technologies, and then also High-Tech Zentrum Aargau for additional funding and discussion, and the company Synthesize for providing us the Q monitoring system. Okay, so I'm open for questions. So we're nearly on time, but I think there's time for questions as well. Or Theo?
We always have time for questions. Thank you very much, Christian. Thank you very much, Silvio. Again, the hint to the participants, if you want to ask a question, please use the raise hand function, which you can find in the participants list below. And so in case you raise hand, your microphone will be unmuted. Additionally, you can write your question in the chat. And so let's see if there are some questions. Seems like there are no questions.
So there's one question from which was sent to me private by Cernchen. I cannot pronounce the name, so it's an abbreviation. Sylvie, you're controlling my.
Yes. I saw it. I'm really sorry.
Okay.
I'm not used to it, to be honest.
So are there interested people?
So the question you got sent, are you reading and answering it, or are you answering it privately in a private message?
No, the question is, can I ask you some questions? So
okay.
Yes, please.
I would say there are no questions at the moment.
All clear.
All clear. And so as there are your contact details also on the last slide. So in any case, everybody can contact you for any bilateral discussions.
Yeah, or maybe Marcel Schubinger, do you would like to tell something about your special material which we used?
Well, I am going to unmute. Are you unmuted, Marcel?
Yeah.
Hello, everybody. Thank you for giving me a short minute here as well. As you mentioned, it's what we call powder preg. We are not actually the manufacturer of the powder preg, but we are the engineers around it. And as Christian and Silvio very nicely showed, these Krelos beamers are just fantastic to follow whatever heat curve you want to do. If you want to heat up for degassing, if you want to have a level where you have flow, resin flow, and then you just raise up to the next level and then you cure it. It's a fantastic opportunity to control your process. And we use that in an application where we think about repair patches on a larger composite structures, or as Christian showed, on the if you just have some parts that you want to accelerate, cure, that are maybe a little bit unhappy for an autoclave. What we saw as well with that kind of material is that you can stepwise cure. So you move your infrared field from, let's say, from the left-hand corner to the right-hand corner, not heating up the full part at one go. This is as well possible that you drive the infrared field on a rail and move over the part and cure it partially, step by step through. So if you have further questions, please either contact Christian or Silvio or myself. We're happy to help you out. Handing back to Christian and Silvio.
Yeah. Okay. Thank you, Marcel.
Thanks.
So there's one question from Serge. Sergey. Sorry. Sergey, I have unmuted you. Okay, so I think maybe you can, if there's a question, you can also contact me via mail by the contact details which are shown on the last page here. Okay, so thank you all for your attention. If there are further questions, please contact Silvio or me. Thanks again also to Theo to give us the chance here in the webinar series to present the results of this research project.
Yes, thank you very much also from my side.